So we're happy to have Niklas with us. And Niklas, I met Niklas a long time ago, maybe at Harvard, when you were giving a talk at some time when you were a student, maybe. And he'll be talking about his pet topic, which he has been working for a very long time, integrability in n equals 4 Yang.
Okay, thanks for the introduction and thanks for the invitation to give a couple of talks here. So what I thought is that I give one introductory talk, which may last throughout today and perhaps some part of tomorrow, and then I will discuss some more technical aspects. Maybe also if you have something specific you want to hear about, I could still put that in and let me know today. But today I will be, as I said, mostly talking, giving a review talk of things that happened in connection to integrability in AdS CFT, leading towards the Yangian Symmetry. Yeah, so this talk will be about integrability in the planar AdS CFT duality, and I will start really slow, although probably most of you will know very well what is AdS CFT. So that's a proposed duality between string and gauge theories, or more generally perhaps between gravity and QFT models. And in this AdS CFT duality, some integral structures have been observed in the planar limit in some particular models, but perhaps the most prominent models. And this integrability is not just a technical feature, but it actually provides a nice toolkit to do efficient calculations of some quantities that you might be interested in. And it has actually been applied to confirm central aspects of the AdS CFT conjecture. So assuming that you still think that AdS CFT is a conjecture, this gives you some more confidence because it does confirm some of the predictions. And within this whole framework of integrability in AdS CFT, the Yangian algebra is an invariance, or serves as an invariance or as a hidden symmetry, which is related to this whole integrability story. So the goals of integrability more generally is to improve our understanding of QFT and gravity in terms of algebraic and analytical methods which are related to integrability, and they give rise to non-perturbative results. And maybe also on a more theoretical footing, it's about the understanding of some more unconventional symmetries that might help us to eventually develop other non-perturbative methods or better understanding of QFT. So in this talk, I will start with an introduction of AdS CFT, and then talk about integrability in this context and its achievements for most of today. And at the very end, I want to tell you in what sense I like to view this Yangian algebra as a symmetry, which relates to more recent work of mine, and this may be sometime tomorrow, or maybe at the very end today. If you're interested in lunch, let me know at some point, because otherwise I might continue talking, at least for an hour today. We can easily go on to tomorrow. Let's see where we get. But let me start by introducing the AdS CFT correspondence. So the AdS CFT correspondence you can view as something which helps us understand strings on curved target spaces, as opposed to strings on flat space. Such string theory has nonlinear equations, and therefore the spectrum of such a theory is in general difficult. And well, when you would be talking about scattering or strings on flat space, that is something that's not quite so straightforward here, because you don't even know how to really start. And the AdS CFT in this context is a major achievement because it relates a string theory, or more generally a gravitational theory, on such an AdS target space to a conformal field theory, which is the boundary of AdS. So we have a very different picture, which helps us to understand some of the aspects of the original model. The prototype for such duality is the duality between two weak strings on Ads5 X S5 target space with n equals 4 supersymmetric Yang-Mills, which is a 4D CFT, and perhaps one of the most interesting gauge theories, or at least has perhaps the richest set of interesting features that you can encounter in a 4D gauge theory. So it is highly symmetric, it's highly accessible, but it's a nonlinear model. Both of these are nonlinear models, and and the problem with AdS CFT is that it's a strong weak duality. So whenever you do computations on one side, you cannot really alternatively access them on the other side, so it's hard to test. Okay, so the two models are strings on Ads5 X S5. Well, this is mainly, or at least the way I will be looking at it, is maps from the worldsheet, from the two-dimensional worldsheet, which is perhaps mostly a cylinder, to the target space, which is this product of an AdS center space in 5 dimensions and a 5-dimensional sphere. On a technical level, it's a 2D nonlinear sigma model. So it's basically a 2D quantum field theory. It has two coupling constants, the worldsheet coupling, which sits in front of the action, and also the string coupling, which is perhaps not so relevant in this talk. It is weakly coupled for large lambda. That's just the way how we define this worldsheet coupling lambda. And the symmetries are basically the isometries of this background space. So for S5, this would be rotations in 6 dimensions. Similarly for AdS5, then some supersymmetries, and altogether this forms a Lie superalgebra PSU 2.2/4. On the other side of the duality, there is n equals 4 super Mills theory. This is a 4-dimensional quantum field theory model. It has a gauge field, it has 4 fermions, 4 types of fermions, 6 types of scalars. The gauge group can be anything, but you would typically choose SUN. And what's perhaps special about this gauge theory is that all fields, that is also the matter fields, are massless, and they are in the adjoint. So all the fields are invariant matrices. That's something you should keep in mind. But apart from that, you have rather standard couplings that you are used to from the standard particle physics. So you have median gauge couplings, you have Carver type couplings, you have to the fourth couplings. But you have only just, again, mostly 2 coupling constants. One is the Yang-Mills coupling, and the other one is the topological angle, which again will not be too relevant. And you have a symmetry. The symmetry is not just Poincare, not just super Poincare, but it combines with conformal symmetry to give this super conformal symmetry, which is also given by this group PSU 2.2/4. So we need some supersymmetry also for the signal to get across the room. It protects the quality of your signal, namely beta is exactly 0 in this n equals 4 super Yang-Mills, but it doesn't mean it's trivial. You still have something interesting to say that you want to communicate. Okay, so, but this is a theory which is weakly coupled when G Yang-Mills is small, and we can compute, basically we can compute anything we want by Feynman graphs, so such objects like that, which are perhaps much easier to draw than to calculate. So that is still a hard problem, maybe not so at the one loop level, but higher loops. And then the third key issue I will be looking at in this series of talks is the planar limit. In the gauge theory, it's the large n limit, so where you take the rank of the gauge group to infinity, while at the same time you take the coupling constant, the Yang-Mills coupling constant, to 0, while preserving the trough coupling g squared n, which is lambda. And in this limit, you will only get planar Feynman graphs. You don't allow for propagators to cross when you draw things on the plane, and that actually leads to drastical combinatorial simplification of your graphs. So many graphs that you could possibly have are just discarded, and actually just the simplest types of graphs survive. And here you can actually see how things already relate to something like string theory, because if you draw the Feynman diagrams on the surface, this surface is roughly speaking is a two-dimensional surface, and roughly speaking the well sheet of the string. And then if you go to higher and higher loops, this perhaps because this surface becomes more and more obvious, because at the end of the day, very high loop orders looks almost like something flat or smooth. So in string theory, you also have a planar limit. That is where you set the string coupling constant to 0, and you don't allow for strings to split or join. So whenever you have such a string vertex where say, a closed string might split up into two closed strings, or two closed strings can join into one closed string, this is governed by the string coupling. And since we set it to 0, these processes will not survive. Okay, so, but nevertheless, this worldsheet coupling does remain in string theory. Okay. Now, finally, about integrability, that's good that the volume has been turned up for that. Yeah. If you wanted to do any computations in a quantum field theory, such as n equals 4 super Yang-Mills, you would usually go to Feynman diagrams, Feynman graphs, but go to higher loops, then that will be enormously difficult, just because of combinatorics, not only, but also because graphs are very, or the integrals that you have to calculate are very difficult. But it's also very difficult, even at lower loops, if you have many legs, and that has to do with the fact that when you have many legs, there's much external data, and the function that this represents will be a function of all this external data, and as such, it's very hard to write something, or you can pop on so many different that it becomes a very difficult problem. Now, the point of all these talks is that n equals 4 super Yang-Mills is apparently integrable, and so is the AdS CFT dual string theory on AdS5 X S5. And this peculiar feature somehow simplifies calculations vastly, and to such an extent that the spectrum of local operators, or the spectrum of string states, is now largely under control, and you can do actual computation. You can compute these observables not just perturbatively, but even at finite coupling lambda to some extent. For example, it does lead to a simple integral equation for one of these dimensions or spectral data, which is known as the Cusp dimension, and which appears sort of all over the place in these theories, and that's something I will show a bit later. So there is an AdS CFT dictionary, what these local operators correspond. When you have a local operator, what you would do is you would take a couple of fields, perhaps with derivatives acting on all n by n matrices. So you take a product and take a trace, and such an object in the string theory should correspond to a state of strings of the string theory, and these states could have various excitation modes or just the vacuum, and that to determine sort of what combination of, or that corresponds to what combination of fields you have on this side. And one key observable on this side is the scaling dimension, local operator in a conformal field theory. A key quantity is the scaling dimension, which tells you how correlation functions roughly behave under scaling transformations. And for example, for any two-point function of local operator, this would scale as the distance between these operators raised to some power and the scaling dimension. And on the string theory side,
corresponding quantity is the energy of these string states. That was a similarly prominent data piece of information for each string state. And these are things you, in principle, want to know, understand, and maybe compare between those two models. So let me outline how that works if you have integrability at your disposal. Okay, so instead of talking about such local operators, it's very useful in the gauge theory setup to talk about spin chain. And in fact, only single trace operators will be relevant. So a single trace operator is something where you have a trace of product of field. And each of these fields can be any combination of the various fields, fermions, scalars, or field strength with some derivative acting on it. Well, let's translate this to terminology of but just goes on two scalar fields without derivatives. So any local operator will be of this form, some sequence of phi1 and phi2s, which due to the trace becomes a cyclic object. And so you could depict it like that. And if you then identify phi1, that should be phi1, and phi2 with a spin up or a spin down state, then you have a state which is a sequence of spins, which are either pointing up or down. And that's what you call an object of a state of a quantum spin chain. Of course, it's a little bit more complicated than that, because you just don't only have these two fields, but actually all other fields as well, and any number of derivatives acting on them, which gives you very many spin or infinitely many spin orientations, which you can choose from there, and then you can construct more complicated spin chain states. But it's just a little bit more complicated. But in this picture, you will be interested in the spectrum of this spin chain. And spectrum is the spectrum of eigenvalues of a Hamiltonian, and you want this Hamiltonian to reproduce exactly as eigenvalues the scaling dimensions that I mentioned here. So to understand what is this Hamiltonian. Now, this can be computed in perturbation theory. Basically, you get a sequence of objects like that, which is a perturbative sequence if lambda is small. And these objects are understood in something like Feynman graphs. So if this is your local operator, so these are the sites of these are the fields or the sites of your spin chain, then Feynman graphs, if you have one loop, if you can close one loop, then these Feynman graphs can sort of close the loop here, there, or there. These are the various contributions you can have in the planar limit at one loop. And what you notice is that only nearest neighbors of this chain can interact through such interactions. And so you can summarize them as the symbol which attaches to two links of your chain and produces two new sides of your chain. It just forms them. Well, as it turns out, not at the first two, at the one level, but then it does, because as Feynman diagrams are, you can, well, for example, so for example, if these are two fermions, three scale at some order, but since each of these that would be a term that fits in here. And then there are some other term which is just sort of the conjugate, and then it goes on and on to higher orders. Yeah, I mean, then this whole spin chain picture becomes more complicated, but you can still call it a spin chain. The nice thing, though, is that if you look at the leading behavior, the leading contribution, that's this one loop contribution, and that is just an interaction between pairs, and it doesn't actually change. Yes, that's since since each of these vertices is a square root of lambda, yes. I guess that's why it is. Yeah, that counts the number of powers of lambda. Why is there no H1? There is some amount of freedom here. You can diagonalize. I mean, at the end of the day, you want to diagonalize the Hamiltonian. Now, you can do this in perturbation theory, and the point is that this here counts the classical dimension. And if you have any contribution here that does not preserve the classical dimension, then you can perturbatively, this is what's called first order and second order perturbation theory. You can remove those terms. And yeah, from first order perturbation theory, you can remove all terms that don't preserve the dimension. And then there is no such diagram that actually of this that does. You could say that, yes. If you do a similarity transformation, that changes the spins. I mean, I guess that's not really what you do when you do Feynman diagrams and say you do dimensional regularization, then all of these terms just automatically are absent. But you could in principle think that these are there by doing some other scheme, say. And when those diagonal terms are there, you can perturbatively remove them to diagonal terms at higher orders. So then you are left to diagonalize this part, and then it becomes a problem of second order perturbation theory and so on. But that, in principle, that's why these terms are not there. Well, the point is, if you are in the planar limit, you could not have an interaction, say, between this leg and that leg, because it would have to cross these two legs in the middle. Or if you do that, if you have an interaction between here and there, the Hamiltonian would actually split up your spin chain into two. And that is, if you look at the large n limit, that's a 1/n contribution. That's like a string splitting one string into two strings is 1/n or G string. And that's something that have only interactions between nearest neighbors. However, if you go to higher orders in lambda, that, as I said, becomes somehow, not so clear, because then you have interactions between several nearest sites, and even the number of sites fluctuates. It becomes a complicated problem. Yes. Although the planar, I mean, if you don't insist on the planar limit, you still have such interactions. They just then interact between various spin sites at a distance. Yes. I mean, in the planar limit. Otherwise, it just tells you how you can have so and so many spins interacting at a distance even. But that even whenever you have an interaction at a distance, that really has to come together. It always has to be a topology change. Only if these interactions are local, then it doesn't have to split or join strings. But maybe the most interesting feature of this nearest neighbor Hamiltonian is that it's integrable. And this integrability apparently remains even at higher loop orders if you have such correction terms, even though it's not quite clear what you mean by integrability in this place. But so what does it help you if the system is integrable? So let me go through, sketch the beta if you want to an integrable spin chain. Yes. Yeah. So so far I haven't really said what is integrability, but one definition of integrability is to say that there are additional conserved charges which also commute with each other, and there needs to be a precise amount of them, I guess. I mean, even in a quantum system, this is not so clearly defined, but if there are more charges than just the Hamiltonian, which commute with the Hamiltonian, then this might be an integrable system. Now, you can construct such charges for this Hamiltonian, and you can then deform such charges by higher order corrections in the same way. And what we've checked is that you can construct such charges for these particular deformations of the Hamiltonian. You can construct them, but you know, depending on some cases, we've looked at some subsectors where it's easier to go to higher orders, and then there might be results up to 3 or 4 loops. There's also a case where you can formally construct this to arbitrary orders if the interaction is of a given kind. But then again, these higher order corrections are not even known for the complete Hamiltonian at all. No, SO6 is not a sector, it doesn't close. Whenever you put SO6, then this remains in a sector, but when you put SO6 here, something else comes out, which you don't like. But there's a bigger sector which contains part of SO6, and that has been done, I guess, up to 3 loops or so. Yeah, I guess at of these talks, there will be some results that eventually allow you to do that. In the meantime, you can find any other proof that you like. I mean, first of all, say for the whole theory, you would have to understand what these terms are precisely. Yeah, that's something for the that's maybe something I will talk about tomorrow and the day after. I think there's some notion of how this works, but it's not an easy, straightforward thing to do or something that you can do with established methods. So yes, I think there will be, but it's not quite formulated. I mean, the fair statement is that I haven't really done too many calculations beyond 1 loop anyway. But I mean, carried out to the end, but still at the structure of Feynman diagrams, and then you can sometimes see some structures, but maybe this is easier to answer later. Okay, so let me give you some. No, okay, you want something else. Yes. No, sorry. I mean, depends a bit. For this part of the Hamiltonian is completely known, and not just SO6, but everything, and that is integrable. Now, I mean, what does it mean for a quantum mechanical Hamiltonian to be integrable? What does it mean? I haven't given you a precise definition, not just because it might be difficult, but just because I don't know of any. So if I don't, I mean, it's hard to say. If I don't know what this thing is that I want to prove, how can I prove it? There's no mathematical proof for something that's not well defined. It might be well defined, and towards the end of the talk, I will give you some idea of what I mean by integrable. And then that is something you can prove, hopefully. But anyway, let me go to 1930 or something and tell you how to obtain the spectrum of an integrable spin chain. And this is the famous Bethe Ansatz. So you would start with an infinite chain, because that makes things easy. You want to be restricted to periodicity issues at first. So you have this infinite chain and you align all the spins so that you're in a ferromagnetic vacuum, and that's a state which you can easily write down. And since we have locality and translational invariance, it makes sense to have momentum states. So you give it a certain momentum along the chain, and for state determine the energy, and that's what you call the dispersion relation of your model. Okay, you take the next more complicated problem, namely you flip two spins, and as long as they are very far apart, they behave like two individual one-particle states. So they have their individual dispersion relations, and they will, propagate along the chain in exactly the same way as this state. But when they come close, they scatter basically. And this scattering process is described by the S matrix, by two-particle S matrix, which is basically a scattering phase factor for all the various particle flavors that you can have. And well, that's all there is to know up to two spin flips. And in fact, you get a very similar picture for string theory if you consider string to be, a string, some piece of string, which at first you just shouldn't make it just stretch. There's nothing interesting. That vacuum. And then you can excite it by putting some localized excitation on it and let it propagate along the string with a momentum. And that again has a certain dispersion relation. And for this model, as well as for this model, you indeed find that there are 8 types of excitations of bosonic type and 8 fermionic excitations of the vacuum. And that's the usual thing you get for a string theory, because, superstrings live in 10 dimensions, but 2 dimensions are eaten up for the worldsheet. So you have 8 directions orthogonal to the string, and then for supersymmetry, the same amount of fermionic excitations. And again, when you have these excitations running down the string, at some point they might meet, and if it's a nonlinear model, then they will do something interesting, and that's again the scattering matrix. Well, this would perhaps be a time delay in this case, but it's still described by a scattering matrix, in particular if you quantize this picture. Now the scattering picture that you get has a certain type of residual symmetry, which you get from the original model, and this is 2 copies of this algebra SU2/2. And this symmetry turns out to be very constraining. In fact, it even determines the dispersion relation completely. You get this funny function which involves, a square root and a sine. And in that sense, if you analyze where could you get this function from, on the one hand, it's a bit like a lattice-like function because, it depends on the sign of the momentum. So you have something like Brillouin zones, periodic wave function which repeats after a certain, after your elementary cell. And that means that basically you're looking at a discrete model. And on the other hand, characteristic dispersion relation is E is the square root of 1 plus something, and this something is p squared, at least when p is small. So it's not quite relativistic, but it's something you might expect from a 2-dimensional quasi-relativistic theory. Okay, and that's not all, but also the matrix structure is determined by the symmetry, and this matrix structure for this matrix, well, you have 16 types of things coming in here, 16 types, so it's a rather big matrix. It describes all cases, but all of these matrix elements are related, and even the overall phase is constrained by some consistency requirement. And the best thing about all of this is that all of this holds for finite lambda. So somehow the symmetry even knows about this coupling constant, and it somehow puts it precisely in this place here and in certain places in the S matrix, and that's completely all fixed for you by symmetry. And just because it's fixed by symmetry, and symmetry is usually a non-perturbative statement, this is something that does hold at finite lambda. Yes. That's the, I mean, yeah, symmetry can't do much better than that. It can never do much better than that. So then, but then again, what is lambda? Yeah, I mean, I think you have a similar issue in both gauge and string theory. In string theory, you know that lambda is the thing that sits in front of the action. This is square root of lambda. It could as well be just something else. Depending on your regularization scheme, it might actually be something else. If you have a different regularization scheme, it might not be square root of lambda, but maybe square root of lambda times 1 plus lambda plus blah, blah, blah. So I think this problem, what is lambda, is the same everywhere. Mm-hmm. Yes. I mean, okay, it has been tested at least to 1 or 2 or 3 loops by explicit calculations. To some amount of loops, you can actually compare this. Always given a certain scheme that you're choosing. Yeah, it just sits there. Yeah, for that you just eliminate this 1 plus, and then it's square root lambda. Yeah, it even fits at strong coupling to some extent. And you might wonder why do you always use just this plain function of lambda being just lambda? I don't know quite. But this lambda also enters this matrix here, and instead of having lambda there, you could always replace lambda by f of lambda, and then it would just put this matrix in a major way, but the results would always be the same up to inserting a function of lambda everywhere. Yes. Okay, that's. I mean, this is the that determines this two-particle scattering matrix. But in fact, there is a much bigger symmetry behind this whole framework. It's a non-local symmetry. It's infinite dimensional. It's a quantum algebra. It's what you call a Yangian algebra. And you can show that this S matrix actually does obey this Yangian symmetry, and also higher particular S matrices obey Yangian symmetry. In fact, it's not quite the usual Yangian, you know, say for for this algebra, it's not the Yangian of SU2/2, but there are certain extensions that are relevant. And I don't think it's really well understood, and we're still continuing our investigations of this algebra and how to formulate it precisely. Yeah, but that's just an aside for now. I will more about Yangians later, so this will come up every now and then. Okay, so this here tells you how this infinite chain or the infinite string behaves, but it doesn't quite tell you anything about the spectrum yet. Well, before we get there, we also have to consider more than two particles. So for that, we need factorized scattering, because integrability implies factorized scattering. And for factorized scattering, you need that the Yang-Baxter equation holds. And that's just to tell that if you want to factorize, say, this permutation process of 1 to 3 going to 3 to 1, then you can factorize this process in two different ways. And this process of the sequence of two-particle scatterings needs to be the same in order for factorized scattering to make sense. And that's the famous Yang-Baxter equation. And indeed, this two-magnon S matrix does obey the Yang-Baxter equation, even though, I mean, it was just constructed by symmetry and it just happened to obey this rather complicated relation. But then we also have to go to closed spin chains. These are the traces, the local operators. And for that, the wave function in a certain sense needs to be periodic. And for that, the momenta must obey the Bethe equation. The Bethe equation is actually not too difficult to understand. What you do is you take this this state, which is now on a closed chain, And what you do is you take one of these particles and just move it around the whole chain once around the full circle. And along the way, it meets all the other particles that live on the chain. And for each meeting, there will be one scattering process, and you move it back to its original position. That should pick up on an overall phase. And this overall phase for a consistent periodic state should be 1 or 0. So e to the I phase needs to be 1. And so that means that the original wave function is just the same, because when you take one excitation, move it once around, you haven't actually done a thing. So this equation needs to hold. And that is one equation for each momentum, and therefore, typically for most configurations of momenta, this will completely quantize the set of momenta. So instead of having, before imposing the Bethe equations, these would be continuous variables, but once you impose them, only certain momentum configurations are allowed, and this will be discrete sets. And that then discretizes the spectrum. It gives you very well-defined energy levels. Yes. Yes. Well, the question here is since you have conserved quantities, the only thing that you can do is a permutation of the part. I mean, you could also, otherwise you could think, okay, you have two particles or several particles coming in with certain momenta, and they will be scattered off in something completely different. But because you have these conserved quantities, the only thing that is allowed is a permutation. Now, the permutation group is generated by nearest neighbor permutations, if you wish. That's one way of generating it, and that would be the two-particle S matrix. And then there is this relation also for permutation group that pi 1, pi 2, pi 1 equals pi 2, pi 1, pi 1, pi 2, and if that holds, then you get a consistent permutation group. Right. So these are the Bethe equations, and importantly, the coupling constant lambda enters analytically. So you can solve the coupling constant is analytically, or if you wish, by any function that you might want to put there, and you plug to state now. So a useful object operators with spin S. This is, for example, yields, and you add a number of derivatives between them so that you get sort of a spin S state. And this is somehow similar also to the situation where you have two operators which are contracted by a short Wilson line, or in the string theory setup, you can have a string which is sort of spinning around its current position with, I guess, a certain spin. A lot is known about these particular anomalous dimensions. In QCD, these operators, these kinds of operators also exist, and they are responsible for scale violation and deep inelastic scattering. These operators feature prominently in the DGLAP and BFKL evolution equations in QCD. And what is particularly well known is that there is a large S, certain large S behavior. So for large S, if S is large, the cusp, the anomalous dimension for given spin scales like the log of the spin, and the coefficient in front is called the cusp dimension. There are certain subleading terms which are also interesting, but maybe the first, this is the most interesting coefficient, the cusp dimension. Now, since we can in principle compute all of these ds from the Bethe equations, we can also compute the cusp dimension. Turns out it's even easier to equations to get something that gives us the dimension. And that's we did. So these. I guess it is, yes. Yeah, it's. Yeah, well, I mean, you have to look at these states with derivatives, and it's not so evident. But whenever you have, say, n covariant derivatives and you symmetrize them, then you have some object which has a very high amount of spin already, and that's what it is. It's just contained in. Yeah. No, it doesn't. The chain doesn't help you very much. It's not that you have n spins which just generate spin n total, but that's just the way this spin chain works. Yeah. Yeah. That is SL2, and this SL2 is conformal, and so in that sense it's also a conformal type of spin, but in this case, if you write it as such, it's just that you have many derivatives, and derivatives have indices, and whenever you have a vector index, the vector indices, but positively symmetrized, then this gives you a spin, like spin 2 is 2 vector indices symmetrized, as in the metric, and so on. Oh yes, there is, but don't ask me. So the Bethe equations in this large S limit, in this particular S limit, generate to a certain integral equation, and it's an integral equation for this function psi of x, and k of x and y is a certain kernel made from Bessel function, Bessel 0 and 1 in some funny combination, and there's also something which convolutes two of these. And well, you know, the coupling constant does appear in this rather innocent way here in the exponent. And the point is, if you find a solution with certain useful boundary conditions, then you can easily read off the cusp dimension as the value of this function at 0. And the coupling constant again just here appears as a scaling, and there, and that does. But you can now compute this cusp dimension. You can do a weak coupling expansion of this this equation. You can solve it perturbatively for small lambda. What does that do? Well, you have to do rescaling, and you'll dimension, and that matches very nicely with the cusp dimension that you also find in gluon scattering amplitudes, which I'll talk a bit about later. And it also, this function, if you expand it instead, or the integral equation, if you expand that instead at large lambda, then you'll find this behavior which starts as the square root of lambda. And square root of lambda is something that you are used to from these spinning string states. So again, that agrees with the energy of a spinning string, including even some of the loop corrections in this string sigma model. Now, that's not all, but you have an integral equation which you can even try to solve numerically at finite lambda. And so you can really compute it. Function which looks like that, rather innocent. It sort of starts here. That is, and goes all the way linear in G. G is square root of lambda all the way to infinity. And well, what it tells you is that you get a rather smooth interpolation between the gauge theory results, which match precisely with this, and the strong coupling results, which with this. Maybe I just give you a sketch. So you have an exact function, or exact numerical function, which is the red function, and perturbative gauge theory results, which are the blue, and the perturbative string theory results, which are the green functions, and they match nicely in their respective regimes. But the red function, you know, follows all the way from one end to the other end. Use result up to some value for lambda, but in string theory you don't actually get a finite radius, but more of an asymptotic expansion. But still, that matches rather nicely here. Yeah. Yeah, this is just plain truncations of perturbation theory. Yeah. I mean, basically, you would take these and just chop it off after some term. It's not that you have to do it, but that's what this graph is. Yeah. But the nice thing is that this red curve, or rather this blue curve here, gives you an exact result in a four-dimensional gauge theory at finite betrothed coupling. It is at infinite n, but it's finite lambda. So from there, because the Bethe equations that I showed you are not actually exact for finite size, because the scattering that you start with assumes an infinite worldsheet, but the actual string states or the actual spin chain states are defined on a finite cylinder, and you can invent other terms which are called Lischer terms, which correspond to virtual particles which go around the cylinder. This is if you have some excitation. Well, I mean, in the picture that I told you, you have excitations which run along this cylinder, but you could also have things that run around the circle. I mean, it's like a thermal circle where you can have excitations. Or you could also say, since this S matrix has a certain finite extent, and if you put it on a finite circle, then the S matrix can sort of start to interact with itself, and that's also maybe another way of seeing it. The equations are quite exact, but there's a nice idea how you can make them, and that's the thermodynamic Bethe Ansatz. The idea here is that, well, you need that space has a finite extent, but time at the end of the day is infinite. So we may as well consider not evolution in time, but evolution in space. So instead of having this usual time evolution in the infinite time here, we'll just take evolution on the infinite line here for all times but one position, to take the evolution around the circle here. And that's nice, because then you can have a scattering problem on the infinite line. And then nicely, you are in 2 dimensions, and you have one time and one space dimension. And by doing a Wick rotation in time and also a Wick rotation in space, you basically recover the same signature. And so sort of you get to this double Wick rotated picture where basically you interchange time and space. And that's called the mirror theory. And it turns out for this model that the mirror theory is much the same as the original theory. So you can use the scattering picture in the mirror theory where you're actually on the infinite line and where this scattering matrix does apply exactly. One trouble is that it does give you exact equations, but these will be infinitely many equations on infinitely many quantities, which are a bit difficult to address. But then there's a whole array of methods from integrable systems to address such problems. There's a TY system with the Rota equations. You can cast Bethe equations as Baxter equations. There are certain quantum curves that play a role, or at the end of the day, you'll do finite nonlinear equations, which are somehow similar to the Bethe equations, but are then of integral equation type. With those equations, you can address any particular state of finite size, most importantly perhaps the Konishi state, which is the first excited state, if you wish, of your whole chain. And then you can compute the dimension or the energy of this state as an interpolation from weak to strong coupling. You again draw a certain plot, and you can also do an expansion. And I'm not sure how far people have gone, but from the equations you can certainly go to 8 loops. I just displayed the first 4 loops here, just because the first 3 terms are perhaps not, still quite regular, but the 4 loop term already contains some zeta values, and then if you go to higher loops, you even find multiple zeta values and perhaps more complicated animals. But that's sort of the peculiar expansion of your dimension, and it corresponds to at least to an 8-loop result. M is 1 to 6, 1 through 6. Yeah. It's just one particular state of your spin chain. Yes, as always, if you have two indices on the same level, you would always sum over them, if it's Euclidean or whatever, or if you decide not to. Anyway, so as a summary, and I think, well, might get close to lunch. Yeah, it's difficult because I think that there was some calculation even for Conici string theory, but you need a quantum. This is some quantum state. Not sure it's easy to obtain. So on your map of the two couplings, I just draw the 't Hooft coupling ranging between 0 and infinity here, and this is 1 over n or G string, which I plot here, and side here where lambda is small, you'll find the classical gauge theory. And the classical gauge theory will actually not care so much about the value of n. You can do classical or 1 or 2 loop gauge theory easily for any value of the rank. For string theory, this more like sits in this corner. The string is small, so that it's not so easy to consider this two-dimensional classical theory on a worldsheet with non-trivial topology. Anyway, when you do perturbation theory in gauge theory, so you do Feynman diagrams, then you can go away from this line at lambda equals 0 and approach the middle of the diagram from that side. On string theory, you can do two things. You can consider surfaces, worldsheet things, but you might as well consider this to be a quantum field theory on a rather trivial worldsheet, and that gives you free quantum strings going in that direction. The planar AdS CFT correspondence lives on this line where you send n to infinity or G string to 0, so that's this line, and that's the line where you have integrability. And the nice thing is that this integrable regime connects the two classical and regimes of the two theories where you can actually do calculations. And that's where these calculations have been done. Okay, now not quite as I thought I might get, but it's a bit up to you when you want to have lunch. Actually, I could go through these next 3 or 4 slides and then stop. Is that good for you? Okay. So there is another topic which is related to integrability, and that's called dual conformal symmetry. And it sort of originated more from the scattering amplitudes perspective, where some additional symmetries had been identified, but then came together with integrability in a useful way. So let me explain what I mean by that. So one key observable in the gauge theory is of course scattering amplitudes, and in the planar gauge theory you want to look at color-ordered scattering amplitudes, planar scattering amplitudes. So you have a scattering amplitudes where the external particles are ordered in a certain way according to their colors, so that always, these are particles which are n by n matrices. So they have two types of colors, and you order the colors or the particles in such a way that one color of the first particle matches with the conjugate color of the next, and so on. And that's what you call color-ordered amplitudes. And a lot of progress has been made in the last 15 years in computing such scattering amplitudes. in terms of on-shell quantities, on-shell methods, geometric methods, and also in terms of integrability. Now, for such a scattering amplitudes, you do have infrared divergences. These infrared divergences originate from the presence of massless particles. In fact, all particles here are massless, and that's why this whole concept of an S matrix is a bit shaky. But once you regularize the theory, you can compute the S matrix, and you do get infrared divergences. And I mean, no. If you have scattering, then the color that flows into your process needs to come out, because color at the end of the day is preserved. Yes, but all diagrams can be ordered in such a color ordered way. It's just sort of a question how you label the particles with 1 through n on the outside as compared to the color degrees of freedom that they might have. You don't win or lose anything. It's just a way of organizing your scattering. And it may be that if you look at the colors, you know, if it's just red, green, or blue, it's a bit difficult. But for large n, there is a more precise way in which this P1 is the neighbor of P2 and P2 is the neighbor of P3. And the single trace color ordered amplitude is one where you have just one cycle when you go through all particles. You can in principle have 2 cycles or three cycles, but those would correspond to single, double, and triple trace states, or to double and triple multiple string states in the corresponding string theory. But I mean, all I want to say is that there's an equivalent ordering scheme in the large n limit also for scattering amplitudes, and we are looking here at the leading color behavior, leading large n. Now, okay, so as I said, you need to regularize, and you get infrared divergences. But these infrared divergences have a certain factorization property, and you know that a generic amplitude at any number of loops with a given set of external momenta factorizes into the tree-level scattering and times some numerical factor which you can write as an exponent. And in this exponent, there's one contribution which is divergent. So this is like one over epsilon. This is like the one loop amplitude, and this just multiplied by some number. And the factorization works in this function here, which carries the divergence of the momenta, whereas the prefactor just depends on the coupling constant. So this is a well-prescribed scheme for the divergent part. And then there is a finite part, which can reasonably depend on both lambda and the momenta. So that's the way this separation works here. And the nice thing is this one loop, this thing here can be computed at one loop order, and this factor here is supposedly the Cusp dimension again. And then there is a finite function, as I said, which depends on both. Now that's similar to the log S behavior. That's ancient wisdom, which is probably proven and certainly true. Now, in all of these calculations, there was one intriguing observation that has been made for 4 particles, for external particles, and even for 5 particles, namely that this remainder function turned out to be finite. Not just finite, it's by definition it's finite, but it's just 0 or just constant. So this function turned out to be trivial, and if you find something that could in principle be very complicated, but then turns out to be trivial, then you wonder why on earth is that so? This result has actually been found through for loops using unitarity techniques. And if it's true, it would actually give you a give you an exact result for a scattering amplitude 4 and 5 finite lambda, because everything is then known, supposing you know the Cusp engine, which we do. And if that's so, why would it be simple? Is there some symmetry that predict that? So can we perhaps compute this exact function for even 6 or more legs? That would be great. Now, AdS CFT also provides a string dual for planar AdS. Namely, if you have such a scattering amplitude, this is supposedly dual to the area of a minimal surface in AdS5, which ends on a null polygon on the boundary. Why a null polygon? A null polygon is something that matches nicely to the kinematics of a scattering amplitude, because you can identify each particle momentum with sort of the segment with each segment of this polygon. You just say the momentum is the difference of the coordinates of the two corners here. Then furthermore, you say the particles are on shell, and on shell in the massless theory means they are massless, the p squared is 0, and that's why these segments are null. And finally, you have momentum conservation, so the sum of all momenta that flows into your scattering needs to be 0. And for a polygon, that's automatically true, because once you go around the whole polygon, it closes back and you get 0. So all the major kinematical properties of a scattering amplitude are given by these features, and so you can convert your scattering amplitude to this geometric object. The identification using AdS CFT uses a certain T-duality of AdS5 X S5 strings, and then you can even, confirm the functional form of this exponent M1 that you have here. That has a nice strong coupling limit, and this has something to do with this area of a minimal surface. But you can even go further. You can even apply now AdS CFT again, because you know that minimal surfaces ending on the boundary are Wilson loops in the gauge theory. So in that sense, a scattering amplitude is dual to a Wilson loop. And the nice thing is that these two things are defined in the gauge theory, can both be computed perturbatively, and so you can do a perturbative comparison between this one and that one. So this is perhaps best as a test of T-duality in the gauge theory, even though you don't quite know what T-duality is in the gauge theory, but let's test that. And this has been tested at 1 and 2 loops quite successfully, so there's a lot of confidence that this works out. Tells us something more, in particular this T-duality tells us something more, because we know that the gauge theory is super conformal, so we have this PSU 2,2/4 symmetry, which I'll just denote all the generators here by this disk, which will become relevant later. Anyway, so whenever you have a symmetry, then the objects are invariant in a certain sense. So scattering amplitudes are supposedly invariant under the symmetry, and scattering and Wilson loops are invariant under conformal symmetry, in the sense that if you move points around using conformal transformations, the expectation value remains the same. But the curious thing is that this is not the right one. So it does the symmetry, if you identify it using those rules here, does not lead to conformal symmetry of that. And conversely, if you have conformal symmetry of that, this doesn't lead to the right transformation rules for the S matrix. And so we have different action on amplitudes and on Wilson loops. And or you could also say you have two different types of conformal symmetries. One ordinary conformal symmetry, which acts on your object as it should. And then you have another conformal symmetry which acts on the dual object, transforms that, but acts on a different way on the original object. So these are two sets of conformal symmetries, and you can say by AdS CFT, they are related by T-duality. And so here, they are also not completely different. There's a certain set of generators on which they overlap. For example, rotations. Rotations will be the same in both pictures. So some of the generators are the same, but some others are not. And a whole tower of new things, new symmetries, becomes an infinite dimensional symmetry, which essentially is this Yangian algebra that I already mentioned before. And Yangian algebra is something that is often related to, or it's usually related to integrability of a certain symmetry, of a certain system. And but well, I'll go on with this Yangian later or tomorrow. All I want to say here is that this dual conformal symmetry does explain the simplicity of scattering amplitudes, because if you have a dual conformal symmetry, as usual in conformal symmetry, in conformal models, you have conformal cross ratios. And all the invariant objects must be functions of the cross ratios. And it turns out there are no dual conformal cross ratios for scattering amplitudes of 4 and 5 legs. You can simply not form an invariant quantity, and therefore these cannot depend on them. And so this remainder function here has to be a function, this remainder function has to be a function of the dual conformal cross ratios, but since there are none, it has to be a constant. And a constant is practically zero, so that's what explains this result. But then, then for 6 and more, there can be interesting conformal cross ratios, and then R can be a function of them, and that's indeed what has been observed. So that leads me to the end for today, I think. And tomorrow I will just then continue with various achievements using integrability. This will largely be a review, but also lead then to the considerations of Yangian symmetry, Yangian as a symmetry of this model. Thanks.